Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Chance Millett-Banks from the Business Review, and I will be your host. It is our pleasure to have NEC Energy Solutions with us today, who will be discussing energy storage on the grid. Today's guest speakers are Roger Lin, Director of Product Marketing, and Reese Foster, Senior Sales Engineer. I'd like to welcome you to our new webinar platform. You'll notice that this webinar is browser-based, so if you disconnect, please click the link that you received via email to rejoin. In order to ask questions, you can send them in via the Q&A widget at the bottom of your screen, or use the questions box at the top left-hand corner of your screen. We will allocate around 10 to 15 minutes at the end of the session to address any questions or thoughts that you may have. There is also a brief survey for you to complete either during or after today's session. This can be found in the red survey widgets. Please use the help widget if you require any more assistance. So without further ado, please allow me to welcome Roger. Roger, over to you.
Thank you, Chance, and welcome to everybody. Thanks for joining us on this webinar where we'll discuss energy storage for the grid. I'll jump right into the first slide. So why do we need energy storage for the grid? I'm sure a lot of you on this webinar have heard about energy storage, and some of you may be very deeply involved in energy storage. But for those of you that are new to the area, new to this new paradigm, what's going on? So right now, global power grids are facing serious challenges. There are a lot of changes happening to the electricity power grid today, including increased renewable generation, which is typically more variable and intermittent than traditional generation, changing load patterns, including distributed resources like rooftop solar, rooftop PV, which is now in the distribution network, peak demand demographics that are changing, and then slowly but surely EV charging will start to impact the grid, and we're already seeing that happen in some urban load centers where EVs are becoming more and more popular. Lastly, to top it all off, are the aging transmission and distribution infrastructures that need reinforcement. So what does storage bring to face those, to help solve those challenges? Energy storage is the most powerful tool for flexibility of power. And last century grids were required to move energy through distance in real time, so supply must always equal demand. Today, we need the ability to move energy through time as well. Energy storage adds this additional dimension. So what I'll do is go through a couple of experiences that we've had at NEC Energy Solutions with grid energy storage, how they're being used in these different applications, and some examples of the installations that we've been able to put into operation. So for the first case study, I'll take you guys all the way down to South America, to Chile, where we'll talk about primary frequency control, where we're using grid-scale energy storage to support existing generation and, as a result, increase revenues for some of those generation assets. So what's going on in Chile? Well, as we know, the power grid must be balanced. Stability in Chile needs to stay at 50 hertz. The Northern Chile interconnected grid, otherwise known as SING, is about 4.6 gigawatts of generation, and the consumption there is primarily the mining industry, copper and lithium mines, in fact. Generators there typically hold back between 3 and 5% of their capacity to provide a service known as primary frequency control down in that region. Just as a note, so people can kind of put this in perspective, the United States calls this service frequency response, and in the EU and other parts of the world, it's known as primary reserve or frequency containment reserve. So what is that function, actually? So what I'm showing here is some of the different frequency control types that are out there, ways to stabilize the frequency on the grid. As you can see, there are different time scales for response to a disturbance in the frequency. There are seconds response in the first few seconds after disturbance. There's responses that take place in several minutes or even tens of minutes after the disturbance. What we're going to be talking about today is primary frequency control. So on the bottom graph, that bottom left blue curve, where the response is almost instantaneous, where generator governors or other fast responding resources, in fact like energy storage, can effectively provide this service to the grid to compensate for disturbances. So as we look again into this particular case study in Northern Chile, a few things have happened to allow energy storage to provide CPF. CPF again is primary frequency control. That's the acronym they use down there to represent that service. So back in 2009, a new rule was approved by CDEXing, which is the authority down there, regarding who or what can provide CPF. That rule allowed battery energy storage systems to offload a generator's CPF reserve generation capacity requirement. So instead of a, let's say, coal-fired generator, which you can see in the picture there, reserving their capacity on the order of 3 to 5%, they could take that obligation and have it be met by an energy storage system instead. So what does this do? It allows that generator to then increase production by increasing their output of energy, and in that way increasing their revenue. So in other words, letting the generator do what it's good at, which is generating energy at its most efficient rate possible, the maximum efficient rate possible, and then allowing that obligation for CPF, or primary reserve, otherwise known as frequency response here in the States, to be provided by a battery energy storage system. So let the battery system do what it's good at, which is fast response, fast ramping, and fast compensation for frequency disturbances. So with that new rule in place, allowing battery energy storage systems to take on the obligation for a generator, we then installed a 12 megawatt GSS, which is what we call our grid storage solution, grid scale energy storage products, in Northern Chile. The first system that we installed was put in place in 2009, 12 megawatts of power, 4 megawatt hours of energy, across 8 battery containers. It has been operational since 2009. Has been recognized as one of the best performing reserve units in Northern Chile. Now that first installation was so successful that a second installation was put in place, this time down by the coast in a location called Angamos in Northern Chile. This one was larger. This was a 20 megawatt, 5 megawatt hour GSS, comprising 10 battery containers and 5 inverter containers, installed about 2 years later in 2011. Both of these systems, again, combined, provide the obligation for frequency response that was previously required of generators. And so those generators are able now to improve their output, to increase their revenues, and ensure an attractive return for their owners. I guess a notable award for this site is that it was a recipient of the EEI Edison Award. So how are they doing in operation? So I've pulled 2 charts from a little while ago that shows the response of the GSS to a frequency disturbance. So in this case, this chart is pulled directly from a CDEXing fault report from June 3rd, 2011. And it shows the autonomous response of the GSS to a loss of generation. So if you look at the chart, this blue line is animated correctly in your screens, you'll see that the blue line represents the frequency, which is normally at 50 hertz in the beginning. Now, shortly into the chart, you see a disturbance where you've got loss of generation, and of course the frequency then drops precipitously. Upon that frequency dropping below the minimum point in a predefined deadband around the frequency set point, the GSS then injects all of its power in to help stabilize that frequency and bring it back in place. And as you can see, after the GSS comes online, putting its power in discharge mode to sort of support that loss of generation, the frequency starts to recover and then eventually recovers past the end set point on the far right of the screen, where the frequency reaches its satisfactory level, and then the GSS then shuts off. Now, one thing to note about this strip chart is that it's not registering the changes in power fast enough to to show how fast the GSS actually responds to the loss in generation. In fact, even though you can see a slope on the red curve, the rise, the actual slope is nearly vertical. The response times of these systems are under 250 milliseconds and can respond very quickly from full discharge to full charge. So that 12 megawatt system I showed before could go from a negative 12 megawatt charging to positive 12 megawatt discharging, so a full 24 megawatts of ramp rate well under a second. My next slide, I'm showing sort of an opposite case where there's a disturbance in the grid again, but this time it's a loss of transmission, a loss of load. And you'll see the same response, whereas the frequency starts to rise above tolerable limits, the GSS then goes into full charge mode, pulling off the extra power, acting as a controllable load to help, again, stabilize the frequency against that sudden disturbance. So how does this impact the owner? Well, the next chart I'll show is a chart showing the output of the generators that are being supported by the GSS. NTO1 is one of the coal-fired generating plants that is being supported by the GSS, by the Battery Energy Storage System, which is labeled BESS in this graph. You'll see that without the BESS, prior to its installation, the average output was somewhere between 125 and 130 megawatts in the black. After the GSS was installed, the output then improved or increased to between 135 and 140 megawatts. We'll look at the same curve for NTO2, again averaging somewhere around 130, and then after the GSS is installed, increasing to about 137 or 136. In total, NTO1 and NTO2 combined, which again are the coal generators supported by one of those GSS systems, increased from 253 megawatts to 266 megawatts, roughly 5% increase. And this increased output represents increased revenue for the generator. And for those of you that know, energy prices in Chile since 2009 have been relatively high, in about the 90 to 120 dollars per megawatt hour. And so this increased output happens 24 hours a day, 7 days a week, 365 days a year, where in the past it was held back for those occasional disturbances in the grid. And so as a business case, this was a very successful and positive one for energy storage, and of course has been operational since about 2009, roughly five years now, going on 5 years. So in summary, primary reserve or primary frequency control or frequency response, because these functions all have different names depending on what region you're in, energy storage can provide this service with faster and more consistent response than other traditional assets. We've seen very high reliability and performance in Northern Chile. The GSS, the two installations that we have in Northern Chile, have been operational with about 94% availability at full nameplate capacity. They successfully responded to hundreds of events. The response speed is consistently higher than the other units in the region. And of course, after that first 12 megawatt system was installed in the Andes Mountains, second 20 megawatt GSS was installed in 2011 near the coast. On the other side of the equation, the thermal generator that these GSSs are supporting have improved efficiency. Previously withheld power can now be increased to improve revenues by 4 to 5%. And I guess as a bridge back to the different markets in the world that rely on this ancillary service to help stabilize their grids, these energy storage systems are a proxy for potential solutions for other parts of the world that are requiring more and more primary reserve or more effective or efficient types of primary reserve, meeting frequency response or droop response requirements. Energy storage can help replace inertia lost from changing loads or generation fleet. And here in the States, FERC Order 794 may set up a new market opportunity for storage in the U.S. For those of you that have been following the order, the NERC has set obligations for frequency response for different parts of the United States or the North American grid, including Canada, and the frequency response primary reserve requirements have increased dramatically and are now going to be obligations for each of the ISOs. So I know we have a lot of material to cover here, so I'm going to move quickly on to our next case study, which is back in the United States, but this time covering frequency regulation. So what is frequency regulation? How does it differ from frequency response? So the way we look at frequency regulation is, again, it's an ancillary service. It's used to reconcile the momentary differences between supply and demand, primarily for managing power flows between and frequency within a balancing area. But it differs from frequency response or the previous case study in one way. The frequency regulation in the states that we are talking about, the ISOs use a dispatch signal. They send out a signal to generators to provide this balancing of supply and demand electricity, whereas in the previous example, these systems, the GSS or the traditional resources, traditional generation assets out there, would respond to disturbances, to measure disturbances in the frequency itself. So there's a bit of a layer of abstraction between the primary reserve or the frequency response from the previous example and the frequency regulation or secondary reserve, as some people call it, or frequency restoration reserve, as we call it in the EU, in this example. Nevertheless, it's a worldwide reliability requirement for electric grids. Frequency regulation is an open commercial market in the U.S. It's developing elsewhere, and it's developing in the EU as part of the NEC for electricity balancing. So what makes the United States case study interesting is that the U.S. has passed an order. The FERC, the Federal Energy Regulatory Commission here, passed an Order 755, which is also known as pay for performance. I'll go into a little bit more detail about why that's important. And the case study here in the states that we're going to cover is in a region called PJM, which went live with this pay for performance order in October of 2012. So what is Order 755 and what is pay for performance? Why is it important? So one of the ways that we like to help communicate the importance of the order is to ask a question. And the question goes like this: which of the following two units received a greater payment in dollars per megawatt for frequency regulation in PJM prior to October 2012? So what I'm going to do is show you two different resources providing this frequency regulation service and how well they're doing it. So this first example is a combined cycle turbine. What you can see on the chart is a green line and a blue line primarily. The green line represents the regulation control signal, dispatch signal that PJM, which is the ISO, provides to the generators that are providing, or the resources providing, frequency regulation. The blue line is the response to that control signal. So this combined cycle turbine is trying to follow as closely as possible what the control signal is asking for. And as you can see, it's fairly good. There's a little bit of a lag, a little bit of accuracy difference there, but for by and large, it has followed that signal fairly well. Now I'll show you a picture of a different unit. This is a steam unit, again, trying to follow the frequency regulation control signal. As you can see, it is far less accurate, and in some cases even contrary to what the control signal is asking for. So the question again, which one got paid more? And I think you guys may already know the answer. So it turns out they both received the same payment for that performance. And so therein lay the problem. Lack of pay for performance leads to inefficiency. While Unit A provided more value to the grid than Unit B, the rules did not reward A, nor did it penalize B. So the solution was basically to change the market rules to recognize that performance, provide a bonus for speed and accuracy, which are strengths of energy storage. Poor performers would get penalties, and if bad enough, eliminated from the market itself. And overall, with greater performing assets doing frequency regulation, fewer resources, fewer overall resources for regulation would be required, thus resulting in a more efficient and less costly method to balance the grid. Next slide I'm going to show is the frequency regulation pricing in PJM. This basically shows you what happened before pay for performance and what happened after pay for performance in the PJM region after they implemented the rule. As you can see, the prices jumped from roughly $15 per megawatt per hour to over $35 per megawatt per hour after the rules were implemented, which made the merchant market for frequency regulation in this region very attractive. So attractive, in fact, that we did install a 32 megawatt, 8 megawatt hour GSS in PJM in a location called Laurel Mountain in West Virginia. It's owned and operated by a company called AES right now. It provides frequency regulation, has been doing so since 2011. The system itself is comprised of 16 battery containers, 8 inverter containers. We installed the external chillers and transformers, etc. And this was also recipient of an award for Project of the Year. I'm going to show you another installation for frequency regulation that was put in place in upstate New York. This was actually located in Johnson City. So for those of you that know the different ISOs, New York is in a different ISO than is a different ISO than PJM. But I'll get into why I'm discussing this in a minute. We installed an 8 megawatt system in Johnson City, New York, again performing frequency regulation there, 4 containers, etc. However, the unit was located in a floodplain, and as you can see in the picture, those containers were put up on pilings. I think they were about 4 feet high to prevent water from entering the containers in the case of a flood. Now, it turns out that they weren't high enough. There was a major flood in September of 2011 in that area in New York, which surpassed the height of those pilings, and the containers had to be refurbished. One good thing to note of it was that even though these systems contained 2 megawatt hours of energy and had 8 megawatts of power capacity, even while flooded, they did not pose a hazard. They shut down as designed and really exhibited no abnormal behavior, even in light of a natural disaster. Anyway, after the flood had subsided, took the containers, had them refurbished, and had them relocated to a different location in August of last year. So they were moved from New York to PJM, the exact same equipment from one location to the next, in effect transplanted from one market where the pricing was okay but not great, to another market in PJM where the pricing was actually very good. And so the transplanting of these containers shows that you can use these energy storage assets as resources that can be moved from one location to the next, and essentially follow those values, I guess the economic values of business cases that make the most sense. Even if things do change after you've installed it the first time, if you find a better business case elsewhere, they can be picked up and moved. And we've done that several times in the past, and this is just one example of the couple projects that we have moved to try and find those value propositions that make the most sense. So in summary, frequency regulation, again, providing fast response, the GSSs providing fast response and high performance are being rewarded. The 32 megawatt system that I described earlier has been operational since 2011 with 99% availability, has been following the fast response, what they call Reg D signal, very, very closely. And again, it's in commercial revenue service. These projects that I've discussed so far are all in revenue service. They are not pilots or demonstrations. They are making money for their owners. In terms of the pay for performance rules, pricing has increased by about 2.2 times since the rules were implemented back in 2012. Prices today in PJM, I think, are in the $37, $38 per megawatt per hour this past month. We do track that. to see how viable these markets are as they sort of mature and the different market dynamics settle in. And then despite the higher pricing, overall PJM has saved on frequency regulation because of these higher accuracy assets like the 32 megawatt GSS we put in place in West Virginia. PJM has been able to procure less, spend less on frequency regulation and still ensure the same level of service because that mix of resources is more accurate, more precise, and faster responding than their previous mix. And this is all due to the rule changes that rewarded high-performing, high-accuracy resources in the market. Finally, the success of the first 32 megawatt GSS we installed was followed by transplant of another 20 megawatts of another 20 megawatt GSS from New York ISO to PJM territory. So I'm going to hand it back over to Chase to present our poll question.
Thank you, Roger. As he just mentioned, it's now time for our first poll question in today's session. So our question and choice of answers is, if you are planning on doing an energy storage project, when do you need it? Within the next 6 months, between 6 months and 1 year from now, 1 to 2 years from now, 2 years out or more, or your final option is, I do not need energy storage right now. So, Roger, just while we give the audience a chance to vote in this poll, can I just ask you, how long does it take to build one of these?
Yeah, so that's a good question, Chance. We've done a lot of projects around the world, and we've done containerized projects as well as projects that go inside of pre-existing buildings or even new buildings. So really, you look at a couple different milestones. One is, when is that project contract signed? When's the kickoff of the project to install energy storage somewhere? And then in our experience, we found that it can take anywhere up to about a year's worth of time, a lot of that time being dedicated to site preparation, groundwork, some of the other, the procurement lead time for the equipment itself. Once the systems are built and tested in our factory and the site is prepared, the energy storage and the power conversion and all the other equipment that goes along with the balance of plant of energy storage can be put on site. From that point forward, it can take as little as 6 weeks to install, connect, and even commission those systems for commercial operations. So it can be relatively quick. The lead time, again, is a lot of it is in the preparation of the site itself and the lead times on the equipment. I don't know, Reese, you wanted to add anything to that?
Yeah. No, that's it really. You're procuring switchgear and transformers and power converters. Those lead times can be quite long.
Mm-hmm.
Thank you both for that. I believe that's now enough time for the audience to have responded to that poll question. So you are now welcome to continue on with your presentation.
Great. So, Chance, I'm going to turn the next half of the presentation over to Reese Foster, who will discuss a renewable project that we've done.
Thanks, Roger. Thanks, Chance. And thank you all again for attending. So we're going to talk here about something a little different, and that's the idea of using battery storage to aid in increasing the penetration of renewables generation. So in this case, we are looking at a project on the island of Maui in Hawaii. And for context, the island of Maui is getting to the point where if all of its renewable generation ran at its full output, and they were operating at their minimum load point on their grid, they would be getting very close to saturated, to full penetration. It's a fairly unique situation. And so because of that, the utility there is very concerned about the volatility that you get from these renewable assets. And in essence, in order to deal with the change coming from renewables, their traditional generators have to respond with a ramp in the opposite direction. So their interconnections are set up requiring more stable output from those renewable resources, in this case a wind farm, and in order to achieve that, the power producer is installing battery systems to meet those ramp rates. So basic overview of the case we're looking at. This is a 21 megawatt facility. Has 24 megawatts worth of wind turbines. They're partway around the island though, so there's a fairly long feeder system there. The utility has a 1 megawatt per minute ramp rate, amongst other requirements which we'll talk about later. We're installing in a coastal environment which introduces its own challenges, none of which aren't engineering sort of simple challenges. There's also voltage regulation requirements, and we're coordinating other assets on that site. So what I'm going to go through here today is largely a discussion about, or an answer to the question, how much energy storage do I need? So there's some pretty detailed modeling that goes into that. It's difficult to give a rule of thumb answer. List of steps here in the process, and in essence, each step in this process is to refine our analysis space, reduce the number of cases that are being considered, or to basically run an iteration where we're getting to a higher level of detail. So looking at the requirements part of this process, again, this is a ramp management requirement for this facility. The 1 megawatt per minute ramp rate you see in the list represented as a plus 1 megawatt per minute and a minus 1 megawatt per minute. There are also other ramp rate requirements there. There's what they would call an instantaneous change, where between their 2-second samples of data, they want less than 0.8 megawatts per minute, and then over longer time frames, there is an allowance to violate the 1 megawatt per minute ramp, but not certain higher limits. And these are basically set up based on what their traditional generation fleet can compensate for. So skipping through a few steps here and jumping into some of the outputs of this, we can see here a couple of different surface plots where we're looking at violations of these requirements for ramp rate based on different power and energy capabilities. Now each point in these grids is the result of, it's an analysis of a year's worth of data, and the system performing its controls response to a specific control algorithm. So part of the process is obviously refining that control algorithm. We've sort of stepped over that part of the process. But of interest here is these two plots are only looking at a month worth of the data each, and we see that different months have a very different sensitivities to the power and energy rating of the system. So they would, in essence, result in very different battery system sizes to meet these requirements. So just zooming in on one of these, so this is that sort of worst case condition, and looking at it on a fairly gross level at just how many violations do you accumulate in the month. We can see that in order to avoid all of the violations, we're looking at a system size that needs to be greater than about 15 or 16 megawatts on the power axis, and about 7 megawatt hours on the energy axis. Now this is a huge system. This is about 75% of the nameplate of the wind facility. So this doesn't seem like a sensible answer. So digging in to the data, there's a key question, and as you look at the data in more detail, you can see that there's certain events that drive a lot of the problems. So in this case, there's one event in January for a much smaller system, so 6 megawatt, 3 megawatt hour system, and at 15% fade, which is referring to as the battery ages and the energy capacity degrades over time. So this is considering a point later in life rather than the installed capacity. So this is looking at an event where we see that at around 150 seconds on this plot, there's a drop in the wind output. So you see the blue trace is the wind generation output. Prior to that drop there, we can see that the grid point of interconnect, the green line, is trending down at the ramp rate. The battery system in red has stepped up to compensate for the drop in wind, the first drop in wind. But at about 150, 200 seconds, there's another drop in wind output, and at that point, because this is a 6 megawatt battery system, it can no longer compensate for that drop. And so the battery system is pegged, and the drop shows up on the grid side. And so that drop violates the ramp requirements. So this is a problem. There's a further problem that at about 500 seconds, because of the length of this event, we can see the dotted black line, which is the state of charge of the battery, has now dropped down to the point where there's no longer enough energy to continue to discharge, and so there's another drop that shows up on the grid side. So this is a single event we can look at, but we understand from here that more energy and more power would be required to meet this. What am I doing for time? Going back to our March data set, in this set we see some essentially trip events where the facility is running close to its nameplate output, but a high wind event causes the facility to shut down, and so essentially you go from full power to zero in a very short space of time. So this is what ends up driving you to these very large storage requirements. So looking into the resource data, there's a few strategies for dealing with this, one of which is negotiating with the utility in order to essentially get an allowance for these very rare events. There's also the possibility to coordinate with the provider of the wind farm to spin down wind turbines when you start seeing high wind events, so that you get a slightly more graceful shutdown. So working from the raw data for the system, you get these rather unpleasant sizing requirements, but then as you dig into it and find where these pinch points are, you can actually substantially reduce the size of these systems. So, sort of summarizing at the end of the process, going back to the modeling steps again, one of the concepts at each step, we talked earlier about reducing the analysis space, but reducing uncertainty is also important. This is presenting the inputs that go into the life cycle analysis for a battery. So batteries are dependent on how you operate them, so that's the power histogram, where in their state of charge they're being operated, and the temperature at which they're operating. Batteries are quite sensitive to temperature. Combining all these with the sort of detailed life models that we've developed over time, we can generate estimates of how the battery capacity will change over time, and make projections out for how that will change as the project progresses. So the slightly more graphical representation of this, the top part of the slide is talking about that whole modeling process, balancing the trade-offs between installed system size and how the system performs over time, how it ages, how many violations you're receiving, and potentially on the right side of this, how do you manage the capacity of the project over time? As the energy fades, do you need to supplement that over time? And then the underlying things that you're trading off from a owner perspective are the capital cost versus the service costs over the life of the project. So the concept that we really like to focus on is selling less energy storage. Don't tell my boss that, but how much storage does my project need? It's never a simple answer. The requirements that are placed on the energy storage vary from the regulatory type requirements. So in this case, the interconnection requirements, the ramp rates, also fault responses and transient responses, but also the underlying wind resource. What's the nature of that wind resource? How many turbines do you have in this facility? How are they spread out across the site? In this case, we had a single line of wind turbines that ran perpendicular to the prevailing wind, so you could actually expect a fairly high degree of correlation between those wind turbines in the event of a wind drop. On a larger facility, it takes time for a wind drop to pass through the facility, so you don't tend to see as dramatic a change. And then you, of course, have to consider the capabilities of the energy storage platform. Different energy storage systems have different strengths and weaknesses. Some batteries cycle very well. Some batteries can produce very high power with relatively low heat generation inside the battery. These things all have to be considered when you're analyzing the required size of a battery system. And then from the analysis side of the people trying to analyze these things, you can throw big computers at these and just tell it to crunch all the numbers forever. And but it's more effective to reduce the size of the analysis space and eliminate cases that you don't need to consider early on. But also, as I was discussing with the wind trip events, getting outside stakeholder engagement can result in bigger impacts than being clever with your controls development and battery capabilities. In this case, working with the regulator allowed us to avoid having to size for these extreme conditions that in the data set were only showing up 2 or 3 times a year, and get to the point where you're reducing the battery size by more than 30%. I gotta stop pushing the keys. So this is an image of the facility, summarizing again, 11 megawatts, which is definitely a lot less than 16. It's still close to 50% of that facility, though, which most people would consider to be high. Again, this is a small facility where the output of those wind turbines can be quite highly correlated. In this case, we're seeing multiple battery containers, inverter containers, a chilled water cooling system, and then interconnection into a 35 kV substation. Beyond the basic battery system here, we also ended up coordinating other assets on this site. So there was a voltage regulation requirement that I paid lip service to earlier. In order to regulate the voltage at the point of interconnection, there's some switched static capacitor banks in the substation yard, as well as the wind turbines have a certain amount of reactive power capability, and our system was responsible for dispatching that capability in order to meet those voltage regulating requirements. So this has been operational since the end of 2012, squeaked in just before Christmas, and met a pretty tight installation deadline with that customer, and so almost 2 years of operation now.
Yep. That's right.
And as far as the performance of that facility, we can see here, this is real operational data, so it explains why it's a little bit noisy. The real world doesn't give us nice smooth curves. But you see that the arrows are sort of highlighting drops in the wind, and I'm not going to guess blue, is it? Mm-hmm. And then the trace at the bottom shows the battery response, which is sort of holding up the facility output. So the point of interconnect power in black. So this is not only compensating for changes in the wind facility, but also auxiliary loads within the plant, as far as the ramp management. But you can see there that it basically holds a smoother response for the facility, meeting the utility requirements here. And I'll hand it back to Chase for our final poll question.
Thank you, Reese. So once again, it's now time for a poll in today's session. I would just like to point out that you can select multiple options here, so please check all that apply before you press submit. So our final question today is, what application do you think you need energy storage for? Ancillary services, renewable integration, transmission or distribution, grid deferral or reinforcements, behind the meter applications, or finally, I do not need or I am unsure of the need for energy storage. So again, while the audience are voting, I'd just like to ask you, Reese, in what applications do you see the most interest in today?
Oh, that's a good question. I'd say interest-wise, it's scattered around. As far as where it makes sense, maybe is the way I'll redirect that. There's been a lot of good research studies that have basically shown the ancillary services markets tend to have higher values. They're not typically very large markets. You look at PJM, the largest interconnect in the US, and you've got maybe a few hundred megawatts of frequency regulation requirement there. So basically the higher value ones are definitely where energy storage is making sense today. Renewables integration, there's a few what I might call boutique cases, island systems that are getting high levels of penetration, are seeing positive business cases. It becomes much more challenging when we start getting down the list into sort of what you might call energy-related applications, where you're so transmission upgrade deferral as a standalone application is very difficult. But if you can hybridize multiple applications and then that upgrade deferral becomes an additional benefit over a base operating case. So no one answer, but ancillary services, renewables integration, those are probably the big ones.
Okay, thank you for that, Reese. I believe that's enough time for the audience to have voted in this poll, so I'm just going to quickly close this poll and move on to our results. Okay, so it seems that renewable integration is our winner there. Would you like to discuss this and the other responses before you continue with your presentation?
Sure. Hang on, let me just get to that. Yeah, I know that there's a lot of renewable integration applications out there, and we're seeing a shift more and more towards solar PV, and to some extent the wind projects as well, looking for storage to augment the capability of that renewable asset. But as I guess I look at the poll, renewable integration with 53% of the vote, ancillary services is sort of neck and neck with T&D deferral reinforcement. So I think people are looking at all different ways to see how energy storage can support or help solve the challenges they're being faced with, whether they're a utility, whether they're an IPP, even if they're just a heavy electricity user, a commercial or industrial site that's looking to manage a utility bill. Makes a lot of sense. And then I think that last answer of I do not need it, or I'm not sure of the need for energy storage. That's a great indicator of how this market is starting to emerge. There's still a lot of uncertainty on what makes the most sense for storage. I think a lot of people out there are hopefully in the category of I am unsure of the need, where I need it the most, and that's where we can help. We do a lot of work helping people understand the situation they're in, whether they're an IPP, a utility, a commercial industrial load center, and see how energy storage can fit best. And Reese went through a lot of detail in optimizing how we optimize energy storage for the application, how we try and have just the right amount to fit your requirements. If you need to last 10 years, you need to last 15 years or longer, or maybe you only want it to last a very short period of time because this is a very special condition. I mean, that all plays into the analysis that we can do. We do a lot of technical modeling of the energy storage capabilities, as well as business case modeling for helping our customers understand what makes the most sense. And so it's a very hands-on approach right from the beginning, when we understand the application to when we come up with a detailed proposal of how energy storage can help you in your situation. We'd of course welcome all the questions related to that and see if there's a way we can help you guys out. Okay, so what's the summary? Okay, so I guess we're coming up on the end of our allotted time here, so I'll just go ahead and summarize. Energy storage, as we've seen the past 3 case studies and applications, can provide very effective ancillary services and really more broadly grid stabilization services to various players on the market in the electricity supply chain, that is. We've got examples both in South America and North America that have already validated the performance and effectiveness of energy storage. They've been in operation for the past 3, 4, or 5 years, and then bring a whole host of benefits to the owners and to the grid at large, including faster response times. These systems can respond again in under 250 milliseconds to an external signal or stimulus. And then in some cases even on the order of 1 or 2 cycles. They have a much higher ramp rate. In fact, it's almost a vertical ramp rate compared to traditional resources. You saw that in some of the charts showing the response of the GSS to disturbance in frequency. You can ramp from, if the nameplate of the storage system is, let's say, 32 megawatts, you can go from negative 32 on a charge site to positive 32 for a full ramp of 64 megawatts within, well under a second. Of course, as energy storage, there's no fuel consumption per se. It does charge off of the grid, so it takes up electricity, but you don't need to provide it any fuel. You don't need to provide any, coal, natural gas, etc. And of course has no emissions. There's no stack to speak of, nothing coming out. In addition, it doesn't consume any water. So for those of you that are familiar with combustion turbines, and maybe in California we have the once-through cooling restriction, you're not concerned about the water. There is no water consumption as well. As far as versatility of the systems, they are very high. They can transplant it, move it to where you need it. You don't have to keep it there once you put it in place. It's fairly easy to pick up and drop into another location. They're versatile, can perform many different applications. We've discussed only 3 here today of the dozens and dozens of different applications that we have treated in the business case and technical modeling analyses. Flexibility is something that we didn't touch upon a whole lot. The battery systems that we provide here, the ones we've shown, are all comprised of lithium-ion type batteries. It's a very modular design. It's a very flexible design. It can be scaled from hundreds of kilowatts to hundreds of megawatts. They're compact, can fit in very tight locations. We've had some situations where we had to put in place energy storage that fits into an unusual footprint. We've been able to configure the systems, again, with the modularity and the flexibility of our design to fit those strange locations, and finally easy to site and permit. So, in summary, I think energy storage brings a huge value in terms of flexibility of power to the grid to help accommodate those changing needs we discussed at the beginning of this talk, including variable renewable generation, intermittent generation, changing demographics. You've got generation in load centers now. You've got higher, more peaky loads depending on which areas you're in. That could be from, let's say, a cluster of EV or electric vehicle chargers. And so as the grid starts to evolve and become more sustainable, we believe energy storage is going to be an integral piece of the toolkit for utilities and pretty much everybody in the electricity supply chain to help manage those changes. So with that, I'd like to just close out with a slide showing the different GSS deployments we've had around the world. Most of them, I guess, in the beginning, we first installed in 2008, were geared for ancillary services, for frequency regulation, for frequency response, or primary or secondary reserve, as we described before. But more and more, we're seeing more renewable integration, as the poll suggested, more people looking at storage to combine with solar, to combine with wind, et cetera. And then even in the T&D support area, where utilities are looking for storage to help defer upgrade costs for sake of 1 or 2 days of high capacity, and then better use the capital that they've been entrusted with by the regulator. So with that, I think I'd like to close it out, and I think we have a couple minutes left for questions. Looks like there's a bunch of questions queued up here.
Yeah, thank you, Roger. We do have a lot of questions in, but I'd just like to remind the audience that if they have any further questions, please send them in via the Q&A widget or by using the questions box. So back to our questions. Our first one is, how does the performance of your storage solution compare with flow batteries?
Yeah, that's a good question. So again, we're using lithium-ion. Flow batteries are what we see as a very different class of energy storage, whereas our systems are very good at the high power and short durations. A lot of our frequency regulation and frequency response ancillary services installations use energy storage with roughly 15 minutes of storage time, storage duration. Flow batteries, as we see them, are really good for the much longer durations. And so the performance is really most evident in comparison of, I would say, the round-trip efficiencies of those two systems. If you look at the round-trip efficiency of lithium-ion batteries versus that of a flow battery, you'll find that lithium-ion batteries are a lot more efficient than flow, especially at the high power, high rates that we charge and discharge them for frequency response or frequency regulation.
Thank you, Roger. Our next question is, do you do project development and/or integration yourself? For example, with BOP, EMS, or any other turnkey project delivery?
Yeah, Reese, why don't you take that one?
Yeah. So this is something that we do depending on customer requirements. We've certainly done turnkey type of projects where we engage an outside engineering house to get sort of locally certified or locally stamped drawings. We certainly manage that process, and we'll deliver a turnkey solution, a single point of interface to a customer. From the customer would acquire the land, and then we would do all of the works related to installing and commissioning the system.
Thank you, Reese. We had a few comments in regarding a PDF version of today's presentation. I would just like to point out that there will be a PDF of today's presentation in the green resource list widget in the on-demand version of this webinar. Our next question is going to be our final question of today's session. So, is it possible for you to speak a little bit about the battery system? For example, the kinds of batteries used, rechargeable systems, and maintenance costs.
Yeah, I think we can probably address a little bit of that. So again, as I described before, we're using lithium-ion batteries. The lithium-ion batteries have a very high round-trip efficiency, capable of high power, long cycle life, long service life. Again, we're designing for 10 years of life. In most cases, they vary up and down depending on each individual situation, of course. The system is comprised of what we call a grid battery system, sort of the DC energy storage system, which is really the core battery system itself. It has a power conversion system that converts DC to AC, acts as the charger for the battery, if you will. And then, of course, there's ancillary equipment such as HVAC, cooling, battery management. There's safety systems as well. We employ a very sophisticated system of fuses, contactors, monitoring of voltage, current, and temperature to ensure that the battery always stays within safe operating parameters. Systems can be containerized or not. We've shown mostly containerized today. But they can be installed inside of buildings. They can be installed inside of custom enclosures. They can be installed pretty much anywhere that can provide a hospitable environment for the batteries themselves to really optimize their service life and their run times. The operations and maintenance costs are really fairly low. We look primarily at replacing air filters, maybe doing some checks of the high voltage, high power connections. There really isn't any maintenance on the order of what you might expect as if you were a lead acid battery owner having to add water or those types of things to it. Lithium-ion batteries we're all very familiar with. We use them all the time, every single day in our personal portable electronics, our laptop computers, etc. Again, no maintenance, completely sealed, they're non-spillable, and are ubiquitous today, which is one of the reasons why we have focused on that chemistry, this particular energy storage chemistry, for some of these large-scale installations. As far as operational costs, I would say, again, let's get back to the round-trip efficiency discussion where your operational cost is really what energy is consumed in the process of storing that energy. Unlike physical storage of goods, when you're storing electricity in a system, whether it's a flow battery or lithium-ion, you do suffer a bit of a loss. So for every kilowatt hour you put in, you don't get exactly 1 kilowatt hour out. You get something less than that. The round-trip efficiency of lithium-ion can be upwards of 90% efficient. And as you look at other chemistries, it certainly starts to drop. You get into 75 or 70 or 65%. So that really kind of plays into our business case analysis on what the operational costs of storing energy would be. So that's a little bit about the battery system itself.
Thank you for that, Roger. So just before I conclude today's session, do either you or Reese have any final thoughts that you'd like to leave with the audience?
Yeah, I guess to sum up, I think we'd like to just impress upon people, especially newcomers to energy storage, for these sorts of applications, whether it's in front of the meter, utility side, or behind the meter, that it's being used today. We've been working in this field for 5-6 years now. We've installed many systems worldwide. We've got over 110 megawatts of experience under our belt, from locations up in the high desert in the Andes Mountains, down to coastal tropical areas in Hawaii. We've installed in any number of different hospital conditions. And the performance of the systems, I think, speaks for themselves. They're doing their job. They are successful projects for their owners. And we look forward to seeing a lot more of those in the future.
Yeah, use this as a resource. Ask us questions. That's what we try to help people understand their problems as opposed to selling them batteries. Again, don't tell my boss I said that. But also, thank you all for attending and giving us an hour of your time.
Yep.
And hopefully we'll see you back for the next one.
Yeah, appreciate that very much.
Thanks, Chance, as well.
So that just leaves me to thank Roger and Reese for what was a great presentation, and thanks to NEC Energy Solutions for sponsoring today's session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned and follow us on Twitter at BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all have a nice day.